Okay, this section we're going to talk about improper integrals. So far, definite integrals had two requirements. The domain of integration was finite, like from A to B, and the range of the integrand was actually finite on the domain. It is likely that we will encounter problems that do not have at least one of these properties, and some examples are given below. These types of integrals are called improper integrals. For instance, this integral right here, we're integrating from 1 to infinity. So it has an infinite domain due to that upper limit. And then this one, this limit has an infinite range because the function increases without bound as x approaches 0 from the right. So before we get started, let's do a little mini review of indeterminate forms and L'Hopital's rule. Okay, so so over here we have these are some indeterminate forms, and that basically just means you can't determine what the limit is if it's in this form. So if you have 0 over 0, or infinity over infinity, or minus infinity over minus infinity, or infinity over minus infinity, and so forth, that's an indeterminate form. 0 times infinity or 0 times negative infinity is an indeterminate form. 0 to the 0 is indeterminate. Infinity to the 0, 1 to infinity, and even infinity minus infinity is an indeterminate form. Now what L'Hopital's rule says is it says suppose f and g are differentiable on an open interval from a to b containing c, but it doesn't have to be differentiable at c itself. As long as the derivative of the denominator is not 0 for x equals c, and if f of x over g of x has the indeterminate form 0 over 0, or infinity over infinity at x equals c, then we can say that the limit of f of x over g of x as x approaches c is the same as the limit of f prime of x over g prime of x as x approaches c, as long as these limits exist or if they equal infinity. So let's take a look at some of these. Okay, so this example here, if you tried to evaluate this, you would get cosine of 0, which is 1, plus 2 times 0, which is 0, and then minus 1. So you'd have 0 in the numerator, and then you would have 0 in the denominator, because 3 times 0 would be 0. So you can't evaluate this directly. You'd actually have the indeterminate form here, 0 over 0. So L'Hopital's rule would apply here, so just take the derivative of the top and the derivative of the bottom. So the derivative of the top would be minus sine x plus 2. The derivative of the bottom would be 3. And now let's see if we can evaluate this directly. Now let x go to 0, and sine of 0 is 0, so the top would be 0 plus 2, which is 2, and the bottom would be 3, so you would just get 2/3. Okay, now this one is the limit of natural log of x over x. Now, as x goes to infinity, the natural log of x goes to infinity, and also x goes to infinity. So this limit would have the indeterminate form infinity over infinity. So in that case, L'Hopital's rule applies. So we'll take the derivative of the top, which is 1 over x, and we take the derivative of the bottom, which is 1. And now if you let x go to infinity, we know that 1 over x as x goes to infinity is 0. So you would just get 0 over 1, which is 0. And then here's another one. If you let x equal 0, you get e to the 0 minus e to the 0, which would be 1 minus 1, which is 0. And in the denominator, you would get 0. So you have 0 over 0, which is an indeterminate form. So we could take the derivative of the top, and the derivative of the top would be e to the x plus e to the minus x, and the derivative of the bottom would be 2. And so now if you evaluate this as x approaches 0, you get e to the 0 plus e to the 0, which is 1 plus 1, which is 2. And then the denominator is 2, so you'd have 2 over 2, which is 1. And then let's see, this one, as x goes to infinity, e to the 3x goes to infinity, and 3x goes to infinity. So that would be the indeterminate form infinity over infinity. So if I take the derivative of the top, I get 3e to the 3x. The derivative of the bottom would just be 3. Then you can cancel the 3's, and then you get the limit of e to the 3x as x goes to infinity. Well, e to the 3x as x goes to infinity is just infinity. Now there are some other indeterminate forms here that you can work with here. So let me just show you what you might do here. The limit of x squared times natural log of x as x approaches 0 from the right, that would simply be x. Well, the limit of x squared as x approaches 0, which is 0, and the natural log of x as x approaches 0 from the right would actually be negative infinity. So this would be the indeterminate form 0 times negative infinity. But if we write this another way, like let's say we write this as the natural log of x over x to the negative 2, so that's another way to write it, then as x goes to 0 from the right, this would actually go to that would actually go to negative infinity, and then 1 over 0 squared, that would go to infinity. So you'd have an infinity over infinity here, and now we could try L'Hopital's rule. So take the derivative of the top, you get 1 over x. The derivative of the bottom would be minus 2 x to the negative 3. And then that's really just minus 2 over x cubed. And so if we flip it over and multiply, we get x cubed over minus 2 times 1 over x. And then finally we can find out that this is just x squared over negative 2. And as x goes to 0, that's going to be 0. Now here's a form that's infinity minus infinity. So here, if you let x go to 0, this first number is going to be 1 over 0, and 1 over 0, so that's going to go to infinity, and then so is this one. This one's going to go to infinity. So since they're subtracted, what we could do is get a common denominator of e to the x minus 1 times x, and then we can combine the numerators. So then we would have with a common denominator, then we would have x minus e to the x plus 1, and then as x goes to 0, the denominator goes to 0, and the top would actually go to 0, so you'd have 0 over 0, and then you could apply L'Hopital's rule. So take the derivative of the top, and I get 1 minus e to the x. Now taking the derivative of the bottom, I'd actually have to use the product rule. So I'd have x times the derivative of e to the x minus 1, which is x times e to the x, and then plus e to the x minus 1 times the derivative of x, which is this. And then so I would have 1 minus e to the x on top and all over this. Now the problem that I have here though is this. If I let x go to 0 here, I still get 0 in the numerator, and I also get 0 in the denominator. So I still get 0 over 0. So I'm going to try it one more time. I'm going to try L'Hopital's rule one more time. So now take the derivative of the top, and I get minus e to the x. And if you take the derivative of the bottom, well, the derivative of this term is just going to be e to the x. And then if you apply the product rule to get the derivative of this, you'll get x e to the x plus e to the x. Now let's try letting x equal 0 now. So if we let x equal 0 now, we get minus e to the 0, which is minus 1. And in the bottom, we're going to get 0 here, and we'll get 1 here and 1 here. So 0 plus 1 is 2. So we get minus 1 over 2, or minus 1/2. Okay? So there is another application of L'Hopital's rule. Okay, to begin the discussion on infinite limits, let's talk about the function y equals e to the minus x over 2. Now technically this cannot equal 0, but it does approach 0 as x approaches infinity. One might think this yields an infinite area, but the actual area is finite. So if you consider the integral here, so if you tried to integrate from 0 to b this function e to the minus x over 2 dx from 0 to b, when you integrate this, you would actually get minus 2 e to the minus x over 2 from 0 to b, and so that would give you minus 2 e to the minus b over 2 plus 2. And if you take the limit of that as b approaches infinity, we can get the result. So take the limit of that. Well, the limit of this as b goes to infinity goes to 0, and so the limit of this would be 0 plus 2, which is 2, which is a finite value. Therefore, this limit, the limit as 0 goes to infinity of that function actually would be 2. And so the next next I'm going to talk about the different types of improper integrals. So the first type of improper integrals I'm going to talk about are the type 1 improper integrals. Integrals with infinite limits of integration we're going to call type 1 improper integrals. So here are 3 examples. First of all, let's say f is continuous from a to infinity. Then this would be an improper integral where you're integrating from a constant to infinity. That would be an improper integral. So what you would have to do is, instead of integrating from a to infinity, you would integrate from a to b and then take the limit of that, integrate that from a to b, then take the limit of that as b goes to infinity. Now, if you integrated from negative infinity to b, then you would integrate from a to b and then take the limit of that function as a approaches negative infinity. Now, where it gets really tricky is when you integrate from minus infinity to infinity, you actually have to do this using 2 integrals. So what we're going to do here is we're going to integrate from minus infinity to c f of x, and then we can apply what we did in number 2 up here for that one, and then we'll integrate from c to infinity for f of x, and then we can apply what we did up here for number 1 for that one, and then we'll be able to get a value if the integral does exist. So one thing you might want to do is you might want to evaluate improper integrals, you might want to graph the functions to see where the function is not defined over the domain in the integral. So I will do this in the videos, but let me just tell you that in the next video, this one I'm about to run out of time, so in the next video I will actually evaluate some improper integrals.